Right, so I'm going to go over the solutions for A through C in this new Division 2 that just came out. I'll go over the solution for D right after. So, pretty mad about this contest because um, I literally got C right after the contest, like right after system test. I submitted it and I got A C. So, no, I didn't need a solution to solve C. I got it right after the contest, which is very annoying because now I'm losing rating. So, um, if I got that, I would have gained like 50 or 60. But yeah, to be honest, I think my performance was really sloppy because my mistake in C wasn't even logical. It was just like an implementation. Like I also woke up late as well, right? So that I got a slow start, and then I was just being really careless when implementing. Like even my implementation for B is just like, what the hell are you doing? It could just be much simpler. Um, and yeah, sleep is actually get sleep before contest. That's what I learned because um, you'll be more active and less careless when you're implementing, and that's what hurt me today. Like all these problems, yeah, they're not too difficult. So we'll start off with A. Little, was really sloppy. I was not in I was not awake. But anyways, no excuses. Let's just get this out of the way. Just a little annoyed. So satisfying constraints. In this problem, we're given a bunch of constraints, and this actually is a very common problem. Like I've seen this before. I've run into this situation. In fact, I think there's a problem, and that's pretty much like you have to do that, and it's also pretty obvious. Just like you have a bunch of conditions, and so obviously for the greater than or equal to conditions, you only care about the smallest one or if you have to be greater than something, right? I mean, you only care about the biggest one, right? Because if you're greater than the biggest one, then you're obviously going to be greater than all the smaller ones. So for out of the one conditions, you only care about the biggest one. And then out of the two conditions, if you're less than something, you only care about the most restrictive one, which is the smallest one. And then for the ones that are not equal to x, um, just like at first I thought it said so at first I was being really sloppy. I thought it said find some integer. Um, so but it's just like find the amount. So all you do is you can go through and check if my bad and check if the third condition, that number, check if it's like as long as like it's if it's within the range, then you have to subtract one. So assume all of them work between L and R, and then if it's in the range, you have to subtract one. So like pretty straightforward problem. This question, for some reason, I don't know why my implementation is actually trolling contest. Again, I told you I was literally just uh, sleep wise, but it is what it is. What can you do? So, um, this one you want to remove at most k elements in the array from the array, um, and you want to multiply most x elements of the array by -1. So, um, I'll always assume the array is sorted, unless otherwise the positions actually matter. So that's obviously a first step. And then if the array is sorted, fix Alex is going to always pick in k such that it will leave a maximum answer. So if k is fixed, if Alice removes a fixed amount, right? Then and it's sorted. If she's going to remove a fixed amount, he Alex, like for example, if you have like A, B, C, D, E, and assume they're all sorted, right? If Alex is going to remove three, right? We know that Bob is going to negate the biggest one. So obviously Alex is going to just remove the three biggest ones. Like obviously she's going to remove the three biggest ones, right? And then Bob is forced to negate the biggest ones because Bob is always looking to negate the biggest elements. So obviously, we're just going to um, remove the three biggest ones. So you try every value to remove, and then after that, it's just like you can speed up like things with like prefix sums. For example, if you're trying to remove three, then you basically just want to um, again, I was being sloppy. You don't even need suffix sums. At first, I was doing suffix sums. All you do is you just need to find, um, like, from this point, you need to find like x elements uh, from the back. and he's going to remove that many. Um, and then once you have that, um, you can just add the prefix sum of A. So that's if he was if he only could negate two, if he could only negate two, then from here you go to this and then negate this and then you add A. So it'd be A minus B minus C, and you ignore these elements. So you'll see what I'm doing in the code. Really, the only one observation, I'm not sure. Again, I was being really sloppy. This problem is very easy. I um yeah, you just assume it's sorted because why not? And then it's a very obvious problem because all you do is fix the value of k. Um, so I was just being very sloppy. So dp of I just represents that if I start at this element, uh, I will negate, I will sum up like this element and then x minus one more elements to the left of me, right? This element and x minus one more elements to the left of me, because I'm going to need that when Bob negates those values because I'm assuming it's sorted. So I find dp of x really easy, just like literally this. And then at first I thought you needed the suffix, so I was being really dumb. You don't actually need the suffix at all. So again, this is sleep. Like I'm literally not just being careless. Um, but yeah, you do need the prefix sums, and then just go through all the take values. If that's going to be greater than k, then break it. But basically, iterate over each suffix, and then you can just find your answer um, pretty easily. Yeah, you can implement it yourself. Basically, the idea is just you fix k, and it's just like obviously I'm gonna like remove the k biggest ones, and then Bob is going to remove because I know Bob is gonna negate the biggest ones, so let me just remove them, and then you can just try like every single value from k, and just use prefix sums to like make it a little faster, and uh, that little extra. So maybe I could have. I mean, the implementation's okay. So C, got this question literally seconds right after the contest. At first I thought that it would time out. So I was negating a solution like that, but then I just coded it and it worked. And I got it seconds after. Like if you literally look at my first submission that I did in contest, and then I have to wait for system test to be over, it's the same exact thing. I just needed to change k to n over k. So pretty annoying here. But I'll quickly explain this because I honestly do not feel like making a very rigorous solution because I'm a little annoyed today. But basically, you have n elements and you want to split them into n over k. Disjoint arrays, and obviously k is the divisor of n. So the first thing is that's pretty obvious is you should iterate over all divisors of n. So there's root n of them. So let's say we have a divisor d, we have some integer d where d divides n. So I think the notation is like this, if I'm not mistaken. Or is it n divides d? I think this is the notation where d divides n, right? So if you have a divisor like that, right, then you know that you're basically you have these blocks, right? You have these blocks, but you have these blocks, right? So let's just to say that there's two of them, right? Two blocks, right? So maybe this is like d is two, just for an example. And these are some elements, right, that we have. Just gonna use a simple example, right? Right. So then you know that A and D must be the same. So put them in a subarray, right? And you know B and E must be the same. So put them in a subarray. And you realize that the question reduces to find find a modulo M such that all these elements are the same. Like that's pretty much the question. Like if you can take an array and find an M such that they're all going to be the same, that's basically what this problem is reduced down to. Because you're just trying to satisfy the first element, they're all the same. The second element, they're all the same. The third element, they're all the same across all subarrays. So you can just think about this. This is the first. This is the second, right? And the question is, uh, can we answer this pretty quickly to see is there an M such that they're all the same. So you look at a small case, obviously, right? Look at small cases. Well, you know that D minus A has to be congruent to 0 mod M in order for this to work, right? And you know that E minus, or I'm not sure why I'm doing this. You know that this is D. See, I'm sleepy, bro. You know that E minus D must be congruent to 0 mod M in order for this to work. So then you know the condition on M is that M it has to divide D minus A. Like that's obvious, right? When you D minus A must be a multiple, so M has to divide D minus A. If this is true, that means M divides D minus A. If this is zero, that's literally what it means, right? So that means that M also divides D minus E or E minus D, and you can assume that D is greater than A, or yeah, just assume this. It doesn't really matter. But just with all some generality, right? Right. So then the idea here is, and if they're not, just take the absolute difference, right? If this doesn't hold. So then the idea is that basically for every subarray, we have these conditions where M has to divide this, M has to divide that. And so if we want to satisfy everything, if we want to satisfy all of these conditions, right, then all we do is we take the greatest common divisor, right? Because we need a divisor to be common to all of them, and we take the greatest common divisor possible, right? And if this quantity is not equal to 1, then there indeed exists some m that's greater than or equal to 2 that works. And so that's done. So now you tried this on a very small case, right? Does this hold? Like, what happens if there's 3 elements? So that is a pretty interesting argument, a question to be worrying about, right? You can maybe implement this if you're just like, it's probably the same. But what happens if there's three, right? It gets a little tricky. So what happens if instead of 2 we have 3 guys? Then what happens is we have B minus A that has to equal to 0 mod M. There has to be an M. Oop, give me a second. That means we have B minus A 0 mod M, and we have, because A and B have to be the same, and then you might just say, well, we know that B and C also have to be the same, so we also have this condition. Um, so we can write out, because they also have to be the same, right? But we also realize that um, C and A, and in this case, just assume, just for the sake of it, just assume that, you know, just assume that it's sorted. In fact, assume you can assume that they're sorted. It doesn't matter. Like, the sorting does not matter. Assume that they're sorted. Honestly, just assume that they're sorted for the sake. Like, with all its generality, assume that they're sorted, right? And that simplifies things, right? You can assume the positions don't matter. But then you know that B minus A, and then you have C minus B, and another condition that you have, and you'll realize that this condition is redundant. Another condition that you have is 0 mod M. You'll realize why this condition is redundant. You'll realize why this condition is redundant. But this is just, you'll have, for this one, E minus D, this guy got to be 0 mod M. And then you have F minus E, this got to be 0 mod M. And then you have F minus D, this got to be 0 mod M. So what we notice is that this is the condition that A has to equal to B, A has to equal to C, B has to equal to A, B has to equal to C has to equal to B, right? These are all the conditions that we need in order for this to work. So if we have multiple conditions, right? In this case, if we have multiple conditions, we know that we need M to divide B minus A. We needed to divide C minus B. We needed to divide C minus A, right? And you can get the idea here. We need M to divide um, E minus D. We need M to divide F minus E. We need M to divide f minus d. So we need m to divide all these conditions. These are all the conditions that m must satisfy. But by observation, you should realize that if m divides b minus a and c minus b, then this condition is redundant because we know that if it divides both of these, then it will obviously divide this one. Because if you add this up, it will cancel and then it will be 0 mod m. If this is 0 mod n, this is 0 mod n, then of course the sum of this is 0 mod m. So this condition is redundant. And it's similar to this, right? This condition over here is redundant. We don't need to consider FD, right? Because this condition is here is redundant. So as you're seeing, and then if you know M has to divide all of these, then you take the GCD of all the differences. M has to be equal to this. You can set M equal to this, right? And then you know that this is true. M has to be M has to divide the greatest, so m has to divide, so m has to be set to this, right? And then you realize that any divisor of m also works, and any divisor of this also works. Any divisor of GCD also works for m, and any, so m just has to be, so m, so pretty much you could say m has to divide this. This is really the condition we have. M has to divide this, right? And now you have all these conditions, right? So then you realize that m has to divide the GCD of uh, of this and this. So basically, what you're doing, is that you might be able to lose me here, but basically, what you're doing is, okay. So let's just start from the beginning, right? We are fixing the divisor of n. We looked at a small case when there's just two elements in each thing, right? That we're trying to make it equal to. We looked at a very small case, right? At like that case, and we realized that the difference has to be m has to divide the difference. And so then m has to divide. So then you just take the difference, and that's all you have to do. Is if m has to divide this and this, then you can just say, if there has to be a common divisor, we just see if the GCD is not equal to 1, right? Similarly to this, right? If it's 3, we realize that we only have to consider consecutive differences because there's a redundant condition. Like a redundant condition is like if you like there's no point, you only look at consecutive, right? There's no point to say this is I and then this is I plus k and then you take the differences here because they're going to be like a chain of cancellation that if the consecutive differences work, then of course this will work. So you don't need to check that. It's a redundant condition. So you only need to check them consecutively if the consecutive differences are a multiple of m, right? Um, and so then you realize that you have m has to divide all these differences, and so then if m has to divide all these differences, then out of these there must be a common divisor to them. So take the GCD. So then you realize that m just has to be some divisor of the GCD of all of them, and then m has to be a divisor of the GCD of all of them. And in order for all of them to work, then um, m can be set as the GCD of all of them, the GCD of all the GCDs. So this is a little bit. We'll make this more concrete if you check my code. So basically, what I'm doing is I fix a divisor, right? So it's really this solve function. So given that I want to split this into k subarrays, then what I do is I recreate the subarrays where I for one subarray, I take the first element of all the subarrays, and then for another subarray, I take the second element of all subarrays, and I put them into each thing, right? And then I take the differences of them. And one thing you should do is you could sort them. Sorting them, it actually didn't, uh, but it doesn't really matter if you sort them. That doesn't really matter. I just sort them because for an example, you can show how they cancel. But it doesn't really matter if you sort them or not. The idea is just that like you can take all the consecutive differences and then take their GCDs and right take the GCDs of all the differences and then add them to that, right? for that subarray, and then take the GCDs again, and just ensure that they're not equal to 1. So that's pretty much the solution. I'll leave, if you don't understand it, I'll leave you to think it. I think I gave enough insight, even if it's not a good explanation. But the idea is that the way you get the solution is obviously you fix a divisor, right, of n, and if you fix a divisor of n, then you know that the first elements all need to be the same. And so just try a small example, right? Try a small example, and you can get to the conclusion that okay, obviously we need this to be, the difference has to be a multiple of m. And then if we have all these conditions, we realize that we don't need to try every single pairing that they have to be the same. We just need to try consecutive, because if you don't try consecutive, it's just a redundant condition, right? As we saw over there. And then once you get that, then you realize that okay, m, if we need a common divisor for all of them, m has to be, we can just check if it's if this is even true, just get the GCD. But then you realize m has to divide the GCD, so then you can just add it and then see. So yeah, pretty good question. This is kind of like a math question, but to be honest, like I still think like it had problem solving techniques where you have to fix some aspect of the problem, then you have to try small cases, and then notice that something is redundant, so you speed it up. So yeah, it is a little math, but like it's not too big of a deal. So yeah, good question. Okay, that's it.